We'll give a lecture tomorrow, the normal slot. So I'm going to give both lectures today. We'll have a short break in the middle, maybe 5 minutes or 8 minutes or so, if anybody needs to use the bathroom or whatever. Between 2 lectures. We're working our way through the marking of the tests. We've got about 2/3 of them done. So I'm hoping maybe next week to have the results ready and have all the moderation done, but maybe the week after that. Okay. But we're working our way through the marking of the tests. And then in my part of the unit now, we've just got this. Yes, question.
Will we get the physicals?
Yes, I think so. Yes, yeah. So in my part, I've just got this one chapter left to do, chapter 5 in groups, and it's quite different to all the calculus type material that I've been doing with you, the sequences, the series, and differentiation, and so on. It's in the area of mathematics of algebra. And so in mathematics, algebra is the study of what I call algebraic systems. It's the kind of structural study of, let's say, maybe number-like systems. And there's a whole hierarchy of complicated structures going by the names of groups, rings, fields, algebras, and so on. We're just going to focus on groups, just give you a little bit of a flavor of the subject. Go through some important examples of groups. You're already aware, though you might have attached the name groups to it, but you're already aware of several important examples of groups from the mathematical objects you've been studying up to. And it kind of looks ahead to one of the 3rd-year units. So one of the 3rd-year units, which I teach along with Jan Bonnier, on group theories and a dance course on group theory. So let's have a go. So we're dealing with sets with operations on them, so-called binary operation. So a binary operation is the term given to an operation that takes 2 things and produces a value. Takes 2 things and produces a third. You're extremely familiar with binary operations. Ever since you started primary school, started learning how to add numbers together, okay, and how to multiply numbers together. Okay, those are 2 classic examples of binary operations on a set of numbers. Take 2 numbers, you add them together, you get a third number. Take 2 numbers, you multiply them together, you get a third example of such an object. Okay. And since coming to university, you've learned about other binary relations, such as addition of vectors. Take 2 vectors, you add them together, you get another vector. Take 2 matrices, you add them together, you get another matrix. Okay? So these are different operations to addition of numbers. Okay? Multiplication of matrices is not explicitly, or it's not the same as multiplication of numbers. So you've encountered lots of other binary operations. And with me, one particular one we looked at, we emphasized when we looked at it, was composition of functions. Composition of functions, more or less doing one thing after another, is an extremely important fundamental concept of a binary operation. Okay, thank you. Okay. So let's launch into it and see the definition of what a group is, the formal definition of a group. Okay. So a group is a pair of things. It's a set and a binary operation. Okay. Typically denoted G for the set of objects, and star or asterisk for the operation. You think of star as an abstraction of something like plus or multiplication. Okay. Now, it isn't any old set in binary operation. There are 4 important properties that we require this pair to satisfy in order to be called a group. You can kind of think of these 4 properties as being kind of the minimum properties that you require for the operation to be mathematically meaningful and interesting. and mathematically well behaved in a certain basic sense. Okay? So let's look at these four properties, and we'll be looking at several examples of them very soon. Okay, but we're just looking in the abstract. So the first property is a closure property. Okay, and this says for every pair of elements A and B, the upside down A for the quantifier for all A, B, and G. So for every pair of elements A, B, and G, when you get the value A star B, think of that like A plus B or A multiplied by B. It's talking about some abstract operation star. But the product A star B is also in G. So that's saying that the set is closed under the operation. Whenever you take pairs of elements and operate and product them together using the operation, you again get an element from the set. You never hop outside of the set. So the set G contains all the products of its elements under the operation. Closure condition. Or sometimes these are called axioms, group axioms, or group conditions. That's what the closure axiom says. Second axiom is called associativity. It refers to when you take products of products. When you form a triple product like this, the product of A with the product of B and C, the associativity condition says you can evaluate it the other way around. First evaluating the product A times B, and then taking the product of this with C. But as long as A, B, and C, as long as your three elements remain in the same consecutive order, reading left to right, the associativity condition or axiom asks that these two evaluations always gives you the same answer. Okay? That's the property of associativity. Two more left to do. The third property is the existence of a special element called the identity. The identity element is a very special property. Identity element E. The property it has is that, so there exists an E and G such that for every A and G, when you take a product of E and A in either order, you always just get the element A. So the identity is this kind of trivial kind of element. You take a product of it with any other element, the other element remains unchanged. The last property is the existence of inverses. Okay? To be a group, your group must contain all the inverses of its elements. What specifically is an inverse? So it says for every element A and G, there exists, just take this to be a complicated name for another element in G. You can read it in English as A inverse, it's read. There exists a special element A inverse, and this other element has the property that when you take it, the product of it with A in either order, it gives you back the identity, the special element mentioned in axiom 3. Okay. So these are the four properties that have to be true in order to be called a group. And if a system G with the binary operation satisfies these properties, then it's called a group. Now we'll launch into investigating some axioms or some examples. But straight away, we can already talk about a classification of the whole universe of groups. Now the universe of groups, the set of all possible groups that there are, is extremely rich and interesting mathematical structure. And mathematicians are still studying it to this day, and it would still be true that we don't have like a complete understanding of the universe of all possible groups. Very vast, and we have various classification results about them, but there's still lots to study. But we can immediately split all groups into two camps: abelian groups and non-abelian groups. Okay? So if the group operation, if it's always true that the product A times B is the same as B times A, then it's called an abelian group. Okay? Several of the examples you're familiar with do have that property. But if it's ever true that a product A times B is sometimes different to the product the other way around, B times A, then it's called a non-abelian group. So abelian is the term for the group. This property, when you talk about the operation, the adjective for the operation is commutative. So if the operation star always behaves like this, we refer to it as a commutative operation. Say that the elements A and B always commute with each other. But the adjective for the group is the set with the operation. The adjective for that is abelian, named after mathematician A. So even just going from those group axioms, you can start to derive some basic facts about groups. I want to get to the examples straight away, so I'm just going to look at the statements here. You can read through the proofs yourself, okay? But these proofs are all applications. These proofs are all applications of the various four axioms, okay? Just looking at consequences that they have. Okay? The first theorem actually says something that's kind of implied in the axioms, but not explicitly stated. But the identity element is unique. There can be only one identity element. Not immediately obvious just from looking at the axioms, but a simple manipulation of the axioms tells you that there can be only one identity element. Similarly, for any element, there's going to be one inverse for it. Okay? You can't have multiple different inverses for the same element. A third property is you've got cancellation law that you can use. Cancellation laws tells you, well, if you ever encounter a situation where A times C is the same as B times C, then you can conclude that A equals B. You can get that by a combination of the existence of the inverse element of C and the property of the identity. So you simply multiply both sides of the first equation by C inverse on the right. That would cancel out the C and give you A. And similarly, you can cancel things from the other side as well. If you had C times A equal to C times B, you could conclude from that A equals B. The fourth theorem, we'll just dwell on this a moment. It's extremely important, and it's something that you're familiar with already from your study of matrices. That in a group, we can say exactly what, or we can draw a good connection between the inverse of a product of two elements and how that relates to the inverses of the individual elements. And it is true that the inverse of a product is the product of the inverses, but you must add the important proviso, it's the product in the opposite order. So the inverse of the product A times B is the product B inverse times A inverse. Now that distinction of what the order is isn't important if you know you're in an abelian group. If you're in an abelian group, it doesn't matter what order round you take the factors in your product. But if you're in a non-abelian group, this is very important. You do have to respect this fact. The inverse of a product is, which is on the left, is the product of the inverses, which is on the right, but in the opposite order. And you're already extremely familiar with that from your work with matrices. The inverse matrix of a product of two matrices is the product of the individual inverse matrices, but you have to reverse the order. You've already encountered that in your study of matrices and linear algebra. Okay. So that's the four group axioms, some initial consequences of them. But I guess what we need to do to make this a bit more real is to start looking at some examples. Okay. So I'm going to switch to the visualizer now just to discuss some examples. Examples of groups. So far, we don't know that groups exist, so to speak. All we've done is we've put up on the page a definition for one. But definitions don't magically bring things into existence. They just describe conditions for naming things. So I guess the most immediately accessible example of a group would be the integers under addition. So you've been familiar with this for a long time. Okay? Ever since primary school. So if you think about the four axioms, we should just we should just satisfy ourselves or confirm for ourselves that this system does satisfy the four group axioms. Firstly, closure. Well, yeah, I mean, we won't worry about the proof of it, but we're pretty familiar with the fact that if you add two integers, you get an integer. Yeah. Take two integers and add them, you're going to get another integer. Second group axiom was associativity. Well, you won't think about how it's proved formally from some kind of axiomatic system, but you're very familiar with the fact that addition of all number-like objects is associative. Addition of integers, addition of rational numbers, addition of real numbers. You've been using that all the time. Good. So well known, or we've always been using it. That addition of numbers is associative. Addition is associative on integers, rationals, reals, complex numbers that you've been studying. So the identity element, what is the identity element here? What is the identity element in this system? Zero, yeah. There is a special integer. There is a special integer, and it has the property that when you add it to any integer, it leaves the other integer unchanged. For all integers a, when you add a plus 0, it's always the same as 0 plus a. It's always a. Yeah. Inverses. You've got an integer a. What is the inverse element of it? Which integer is the inverse? Minus a. Minus a. Yeah. For any other integer, for any integer, when you add its negative to it, then that gives you back the special element, the identity element, namely 0. Yes. That's a plus minus a. In fact, when you're talking about the integers under addition, you don't use this superscript -1 notation. You use the negative notation to talk about integers. In fact, we don't really use the A inverse notation. When it's more natural to use additive notation. The additive notation for an inverse would be minus A. It's green pen, in case you're wondering. So yeah, so Z plus is a group. What about the integers under multiplication? Is this a group? Well, you can start going through the axioms. Closure is fine. Integer times an integer is always an integer. Associativity is similarly fine. Multiplication of your familiar number-like objects, integers, rationals, real numbers, complex numbers, all those multiplications are associative. Got triple product. Doesn't matter how you evaluate the pairwise products, it's always just going to be the same, just the product of all three. An identity element, is there an identity element? One, yeah, the integer 1. Okay, because for every integer a, you multiply a by 1, it's always the same as 1 times a, that's always a. So inverses. What's the inverse of an integer a? Okay. So should we say that there exists an inverse? Yeah, not within the system of integers. So there is a tempting inverse object floating around that we're aware of, the reciprocal. And most of the time, the reciprocal of a number is another number. But yeah, this is the crucial observation. But the inverse element is not an element of the set we're talking about. And the inverse axiom asks for every element to have an inverse within the system. Okay? Maybe put a little caveat on that. There is a couple of times, a couple of special cases for which the reciprocal is an integer. Plus or minus 1. If a was +1 or -1, those integers are slightly special in that their reciprocals are integers. But for every other integer, the reciprocal is not an integer. And even 1/0 just means nothing. It's undefined. I mean, you might like to say it's infinity, but then you're already way out of, certainly not in the set of integers. Okay, you can take something and divide it into 0 parts. So our conclusion is that this system is not a group. Okay, because it breaks condition 4. So by considering the axioms, by considering the 4 conditions, we find many number groups made of familiar number-like objects. Well, addition will always give you a nice group. The rationals under addition, the real numbers under addition, the complex numbers under addition. Multiplication, once you get to the rational numbers, multiplication will form a group, but you just need to get rid of the rational number 0. Okay? To get rid of the rational number 0, you've got a multiplicative group of numbers. You can check the other 4 axioms, and you will find that they are familiar facts about multiplication on the rational numbers, and indeed on the real numbers and the complex numbers as well. As long as you omit the real number 0 and the complex number 0, it's the set difference notation, then these systems form groups as well. So the reason you need to get rid of 0 is because 0 does not have an inverse in the system. It does not have a multiplicative inverse. 0 does have an additive inverse. What's the additive inverse of 0? What's the inverse of 0 under addition? 0. Yeah, it is its own inverse. There's nothing that says an element can't be its own inverse. Indeed, the number 1 is its own multiplicative inverse. And the number -1 is its own multiplicative inverse. Sometimes elements can be their own multiplicative inverses. And all these groups are all abelian. These operations, addition and multiplication of numbers, we're very familiar with the fact that those are commutative operations. But now I don't want to give you the impression that all groups are these number-like groups. That's really not the case at all. And indeed, as groups go, these groups aren't particularly complicated. Their structure as groups, I mean, certainly the real numbers, the complex numbers, and the rationals, and the integers have lots of interesting structure in them, but just considered as bare groups, they're they're maybe not that complicated. So things really get interesting when we start to look at groups arising in other ways, not out of number-like objects. Okay. The more interesting, of course, these are all infinite groups. The underlying sets are infinite. The more interesting finite groups arise in other settings. And we're going to discuss a key example here, okay, which is very different to those number-like systems here. Okay. So the term for these are called dihedral groups. Dihedral, dihedral groups. What these are the symmetry groups. I'll explain this terminology now. These are the symmetry groups of regular polygons. Polygon is a two-dimensional shape made up of straight lines. The regular polygons are the nice symmetrical ones. The ones all of whose sides are of equal length. So we've got the triangle, the square, the pentagon, the hexagon, septagon, the octagon, the nonagon, decagon. Okay, just any number of sides. Now these are all, so the regular refers to the fact that the lengths of their sides are all the same. All the angles are the same. All of these objects, the man on the street and the woman on the street would say these are all symmetrical objects. They've all got lots of symmetries. They aren't just kind of random shapes. There, when you look at any one of them, got pleasing symmetries to it. Well, we can pin these symmetries down and get very specific and talk exactly about what their symmetries are, and we'll see that the collection of the symmetries of any one of these forms a group. These are important classes of groups. So we're going to consider symmetries of the triangle. So we're going to give ourselves sketch a nice regular triangle. So this should have all three sides the same. It's probably not a great sketch. This base is a little bit short, I'd imagine. We're just going to assume that that's a regular triangle. Now the symmetries. There are two types of symmetries. There are rotations around the origin. So imagine our triangle is centered on the origin. So you can rotate your triangle around the origin. And we can reflect the triangle, reflect in a line. So those are the two types of transformation. So what we're looking at is functions of the plane, transformations of the whole plane that show the symmetries of the triangle. Okay? So they move these various transformations, they'll move the individual points in the plane around. But what they will do, so once we pick them out and identify them, there are certain transformations that while they move all the individual points around, the whole shape of the triangle will still appear the same after the application of the transformation. So for instance, we can have a basic rotation R, which is rotation by a third of a full turn, 2 pi over 3 radians about the origin. Okay. So if you rotate your triangle by a third of a turn, it's still going to be the same triangle you're looking at. Okay, 3 sides will still be the 3 sides of the triangle. You can also rotate it by 2/3 of a full turn. I'm going to call this rotation, for reasons become obvious, but I'm going to call this rotation R squared. So this is rotation by 2 times 2 pi over 3 radians, so 2/3 of a full turn. We'll talk more about the meaning of the power, the meaning of the exponent of the r in a moment. But we could also kind of go for r cubed. So that would be, well, what would that be? That would be a rotation of 3/3 of a full turn. Well, that's really equal to, if you rotate the whole plane by a full turn, full complete turn, every point is back where it started. Yeah. So it has the same effect on the plane as not rotating it at all, rotating it by 0. So i.e. this is what's called the identity transformation, and it will be the identity element in the group. So it's maybe better to call this E, not R cubed. R cubed is a bit obfuscating. It's better to call it E. So we've got 3 symmetries now. We can do nothing to the plane, the identity. It doesn't move anything around. We can rotate it by 1/3 of a full turn and 2/3 of a full turn. So we've got 3 rotational symmetries. One of them is the kind of trivial rotational symmetry, which is in fact the identity.
Is that the same? You know, you're saying all the points end up back at the same point. Does that then obviously then imply that closure is also there because of that reason?
No, well, no, the closure is going to come up in a minute when we, because I haven't really explicitly said what the group operation is for yet. I'm still just trying to pick out the elements. So we'll come back to that issue of closure. Now, what reflections are? There are some reflections as well. There are actually three lines of reflectional symmetry through this regular triangle. Okay? They are each of the lines that go through a vertex and the midpoint of the opposite side. Okay? So these are all lines of reflectional symmetry of the triangle. We'll just label these 3 lines as S1. Call this one S1, call this one S2, and S3. So these are three reflection symmetries, and they're each reflections through the lines shown. You can take your whole plane and reflect it through this line S3. So you send every point through to its partner point on the opposite side of S3. That will again be a symmetry of this triangle. You'll still be looking at the same triangle shape drawn on the plane after you've reflected the plane through S3, through this line S3. So I'm using S1 to refer to the reflection and to label the line as well. Now these are, without getting into the fine technical details, but it's fairly easy to appreciate, and these are all of the symmetries of the triangle. Just considering symmetries as rotations and reflections, these are all of the symmetries. Okay? Just these 6 elements. The identity transformation, the other 2 non-trivial rotations, rotation by 1/3 of a full turn, 2/3 of a full turn, and these 3 reflection symmetries. So these 6 transformations are the elements of D3. The elements of D3, which is the dihedral group with dihedral group of index 3. So it's the group of all symmetries of the regular triangle. Now, okay, this question of closure you raised. What's the operation? I haven't said explicitly what the operation is. See, the elements that we've got are transformations of the plane. They're functions on the plane, basically. These are transformations. Transformations of the plane R2. So we don't add transformations together. We don't. They're transformations of R2, so they're really they're functions R2 to R2. You rotate the whole plane, sends every point in R2 to another point of R2. You reflect the plane in a certain line, sends every point to, again, to a point in R2. So if we've got a collection, a nice collection of meaningful functions from R2 to R2, it's not like we're going to add them. It's not like we're going to multiply it. The natural operation is to compose them. So to take a pair of these things and run one of them after the other, compose them. So the operation is composition, just like we studied in chapter 3 on functions. Composition of these functions. Because from the concept of a symmetry transformation is something that leaves the shape unchanged. So then if you compose two of them, you apply the first one, it leaves the shape unchanged. You apply the second one, it leaves the shape unchanged. So that means the composition of the two transformations, again, leaves the shape unchanged. Applying the first bit of it leaves it unchanged. Applying the second bit of it leaves it unchanged. So we have this fundamental idea that composition of symmetries is a symmetry. This is the closure. This is the closure axiom. The fact that when you run two symmetries together, run one after the other, apply to the plane, after each one you see your shape unchanged. You still see the same shape. So when you regard the composition of the two functions as a single function, it again must be a symmetry. So that kind of gives us our closure principle. D3, it must be that D3 is closed under composition of the functions. Composition of, now this is a universal fundamental fact, composition of functions is always associative. The second axiom. It's nothing particular about the triangle, it's nothing particular about symmetry transformations, it's nothing particular about the plane. Doing one thing after another is an associative operation. You've got three actions to do. As long as you do them in the same order, first one, the second one, and the third one, it doesn't matter how you compose them. In the binary sense, the triple composition is always the same function. It's always the same as doing the first thing, then the second thing, then the third thing. The identity operation. Well, I've already kind of labeled it. That's E. The identity transformation is the identity transformation. The transformation of the plane that does nothing to the plane. It sends every point in the plane to itself. Inverses. Well, the inverse of the identity is always the identity. What's the inverse of R going to be? Right?
Rotation counter to whatever way you
Counter to the, yeah, okay. So R is rotation clockwise by a third of a full turn. You're saying the inverse is rotation counterclockwise or clockwise by a third of a full turn. But in the language of these elements, which one of these elements is it? Well, you see, you're naming one that isn't there. I want you to name one of these 6, because the system is supposed to be closed for inverses. Every element is supposed to have an inverse in it. S2, R2. R2, any other candidates? Want to bat one out?
I'm getting about it.
Think again about it. See, if you, so we're talking about inverses. So we're talking about the operation of composition. So if it's S2, that means you're going to rotate the plane and then reflect it. But we want this to be the identity element. We want this to be the same as the identity transformation. But if you rotate the plane a bit and then reflect it a bit, ultimately you'll have reflected the plane, and that's a non-trivial transformation. It's not the identity transformation. So yeah, the inverse of R is going to be R squared. Because if you rotate the plane by 1/3 of a turn, and then rotate it by 2/3 of a turn, what's the overall effect? The overall effect is every element, every point has returned to its original position. It's gone 1/3 of a full turn, and then 2/3 of a full turn. So it's gone on a full turn, so it's equivalent, that's equivalent to going nowhere. Staying where you start. So what does that tell us about the inverse of R squared? What should that be? Should be R, yeah. You rotate the plane by 2/3 of a full turn. If you want to use one of these named symmetries to return it to its original position, you just rotate it by another 1/3 of a full turn. What about the reflections? What's the inverse of a reflection? If I reflect the whole plane in a line, how do you get every point back to where it was? How do you get the identity transformation? By composing the reflection with another transformation. Yeah, so you do exactly the same reflection again. So that's why I index this one as I, because we can do all these together. So SI inverse, the inverse of S1, S2, or S3, is just the reflection itself. So the reflections are self-inverse. Okay? And that's a kind of universal fact about reflections. If you look in the mirror, you're looking at your mirror image. You wink your right eye, your reflection winks their left eye. But if you've got a second mirror, if you look at your image bounced through 2 mirrors, then you're looking at your original self. Because if you wink your right eye, your reflection winks their right eye back at you. Right? So a reflection, the same reflection of a reflection is the identity transformation. The identity transformation. That's really because when you look at yourself in a mirror, you're not looking at your image flipped left to right. You're really looking at your image flipped. Your whole body has been reflected back to front in a weird kind of way. It's like your whole thing has just been pushed. Your head has been pushed through itself. Kind of effect. Anyway, so that kind of what we've done there kind of confirms the axioms. All of this confirms the axiom. So D3 with composition is a group. And you can equally well play this game for D4, D5, D6, D7 at any of the regular polygons. But really we still don't know much about the group, or we know a lot about the group. We still don't know everything about the group. You can see all the structure of the group with its multiplication table, what's called its Cayley table. They're named after a mathematician, Cayley. The Cayley table, you can, in principle, generate any of these for any group. Cayley table is a multiplication table for the group. When I was in primary school, they used to get us to do these things all the time. Bring in a cornflakes packet, use the other side of it, the blank side of it, and write out addition tables for all the numbers, or multiplication tables for all the numbers. Okay. But we can do this for groups as well. So the idea here is that, and we have to be very careful here. So we'll have elements Gi and Gj. So we'll have an element being a row label and another element being a column label. In the intersection of them, what we do is we put the product Gi composed with Gj. Now we have to respect the thing here. So the row index goes on the left, the column index goes on the right. This is important because when we looked at composition of functions before, we made the crucial observation that in general, composition of functions is not commutative. Doing one thing after another, it makes a difference the order in which you do them. That's just universally true. Remember the example of making a cake. You mix the ingredients and then you bake the mixture. You get a nice cake. But if you bake the separate ingredients first, you get melted butter, burnt flour, etc. And then you mix those melted ingredients, you don't get a cake, you just get a mess. So composition of functions is inherently non-commutative in general. So we've got 6 elements, so we've got 36 entries in this table to fill out. This is really the aspect of a group. So far, we've really just considered this set of 6 elements. You really start to see the group here when you start to see all the group products. Now, the first row and column are easy enough because they refer to compositions of the identity with another transformation. But it's clear that if you compose a transformation with the second operation of doing nothing, it's just the same as doing the first operation. The identity transformation is a transformation that leaves everything fixed. It doesn't alter the other one when you do it in a composition. Equally well, if you do the identity first and then another operation, it's the same as just doing the other operation. So the first row and column in the body of the table are just copies of the row and column labels because those are compositions with the identity element. Things start to get interesting when you look at products with non-identity elements. So remember, in each entry here, we're doing the symmetry, the row label after the column label. So what's R composed with R? R squared. Yeah. Rotating by 2/3 of a full term. If you rotate R after R squared, you get the identity element, yeah. So R after R squared. So you rotate 2/3 of a full turn, and then you rotate an extra third of a full turn. That's 3/3. It's a whole full turn, which is the identity transformation. If I reflect after applying, if I rotate R after applying reflection S1, which symmetry is that? But that's not immediately obvious in your head.
When you're putting R with S1, which one comes first? Is it assumed that S1 will come first?
Yeah, because it's, as I wrote, it's always the row label after the column label. Yeah, so this entry here is going to be R after S1. So what does R after S1 equals? Well, it must be a symmetry because we've indicated that general principle already, that a symmetry after another symmetry has to be a symmetry. So this R after S1, it must be one of those 6. Must be one of those 6 symmetries we listed. We can figure out which one with the help of some labels. So I'll use labels ABC for my triangle. And we'll try applying these symmetries. Now I'll need my original diagram. I'll need to remember how I labeled my symmetry axes. So if I first do reflection S1, where do the vertices move to? Well, see, A remains the same because it's on the reflection axis, but B and C swap. So C will be over here and B will be over here. That's where the vertex points move to. If I then perform the operation rotation R1, so this was rotation counterclockwise by 1/3 of a full turn, but I'm applying it to this triangle here. So this moves the vertex labels around A, C, B. But now we can see here, this is the composition, R after S1. So you look at this triangle, compare it to this one, and pick out which of the 6 symmetries has been applied here. So comparing the first triangle straight to the last one, you see that the vertex C is still in the same position. The other 2 vertices A and B have swapped over. So that the overall composition must be the reflection S2. Is it S2? S3, excuse me. This one that fixes C and swaps B and A. See that there from the first triangle to the last one. So this is S3. Rotating after reflecting in that axis gives us reflection in the S3 axis. So this would be S3. Okay, we'll take a short break now. It's now 11:53. I'll begin again at 12. So if you need to pop out, come for a break, back here 12, or if you want to just stay there and you can be working on completing this table. Okay, so we'll continue by completing this table. When we did every row also be times each other. So every row yeah. And yeah, that talks about how really representative
if you're that's what you have to do. Ring theory is where you've got a group type operation and then a scalar, or then a multiplication. But you have like in groups
So in a ring, you have two of them. You have an additive identity and a multiplicative identity. So So the real is a ring under regular addition. The field is a ring where the multiplication is where the multiplication is. The number of objects tend to always be because multiplication and addition is number of things. You get interesting non-empty.
When you have more operations.
have more. They tend not to be studied so much. In pretty but I mean, it turns out the most natural ones that occur to us are
It's a huge field.
Okay, we'll start again in a few minutes.